Bismillahirrahmanirrahim. I'm Nabila Kossar, student of MS Chemistry at University of Management and Technology Salkot campus. Today I'm gonna present a topic of advanced analytical chemistry, and that is FTIR. FTIR stands for Fourier Transform Infrared Spectroscopy. In this lecture we will discuss about what is FTIR, instrumentation of FTIR, different components of FTIR and its processing, including advantages, disadvantages, and applications in various fields. Along this, we will also discuss why FTIR is more preferable than IR spectroscopy. So, FTIR is a powerful analytical technique that analyzes the interaction of infrared light with a sample. When IR light interacts with the sample, vibrational frequencies are produced, and these vibrational behavior of molecules are analyzed by the FTIR, and it helps to characterize different substances. The basic idea is that different chemical bonds vibrate at characteristic frequencies which correspond to specific wavelengths in the infrared region of electromagnetic spectrum, and that usually ranges from 4000 to 600 centimeter inverse. So let's discuss about components of FTIR or instrumentation. Infrared source, interferometer, beam splitter and mirrors, sample compartment, detectors, Fourier transform processor. We will discuss all of them one by one. This is the basic arrangement. Here is the IR source, beam splitter, two type of mirrors, moving mirror and the fixed mirror. Here is sample compartment. After sample compartment there is a detector, interferogram, and then spectrum is produced. Let's discuss one by one all these components. So first component was infrared source. It provides a broad spectrum of infrared radiations that interacts with the sample. So common sources are glober, which is made of silicon carbide rod, and Nernst glower, that is ceramic rod. Number 2, interferometer. Interferometer is the core of FTIR, and in this case Michelson interferometers are used. It consists of a beam splitter, a fixed mirror, and a moving mirror. Its function is to split the infrared beam into two parts, then recombines them and creates an interference pattern that is called interferogram. First component was beam splitter. Beam splitter is usually made of material like potassium bromide and calcium fluoride. Its function is to split the incoming infrared beam into two beams of equal intensity. Then there are mirrors. Mirrors are of two types, fixed mirrors and moving mirrors. Fixed mirrors reflect one of the split beams back to the beam splitter. Moving mirror moves back and forth to vary the path length of the second split beam, creating an interference pattern when the two beams recombine. Sample compartment. Sample compartment is actually a compartment which holds the sample that is to be analyzed. The infrared beam passes through or reflects off the sample. Then there are detectors for the detection of IR spectrum. Measures the intensity of transmitted reflected IR light. Common type of detectors that are used in FTIR are DTGS, deuterated triglycerine, sulfate, and MCT, mercury cadmium telluride. Then there are Fourier transform processors. This is actually a computer system that applies the Fourier transform algorithm. This Fourier transform algorithm is actually a mathematical equation that works on the pattern and convert it into the Fourier transform or interferogram. It converts the raw interferogram data into useful or usable infrared spectrum. Then there is display and output. The processed spectrum is displayed on a computer screen. The data can be further analyzed and interpreted to identify the sample's molecular composition. This was all about the components of FTIR. Instrumentation and processing. Here is an IR source that we have already discussed, which it will be. So the beams are produced from IR source and they are reflected towards the beam splitter. At beam splitter, the beam of light is splitted into two compartments. One goes towards the stationary mirror and other goes towards the moving mirror. This moving mirror moves continuously, and after going there the rays come back. Reflection is produced by the mirrors and the rays, both rays come back. Here they recombine and the recombination results in a specific interference pattern. After the interferences are produced, the interfered rays are passed through the sample and then to detectors. After detectors, an interferogram is produced, which is further processed by the computers, and then we get an output that is called the spectrum of FTIR. So in the processing of FTIR, first step is beam splitting, which is carried out by the beam splitter. The infrared source emits a broad spectrum of light towards the beam splitter. The beam splitter divides this light into two beams of equal intensity. When the light goes toward mirrors, it is of equal intensity, but when light comes back reflected from the mirrors, one of the beam is of different quality because of this moving mirror. The beam splitter divides this light into two beams of equal intensity. This phenomena is reflection. The beam directed towards the fixed mirror is reflected back to the beam splitter. As I discussed earlier, so reflection reflected back, but its path length varies. Why it varies? Due to this motion of movable mirror. It moves back and forth and we can tune or control the wavelength or interference pattern by the motion or movement of this movable mirror. Next, interference. There are two types of interference patterns that are produced. The two beams recombine at the beam splitter and create an interference pattern. The interference pattern depends on the difference in the path lengths of two beams, which is controlled by the position of the moving. Number one is constructive interference. It actually produces when the path length difference between two beams is an integer multiple of the wavelength, resulting in a maximum intensity at the detector. Suppose this is the first wavelength that comes from the stationary mirror and this is the second one that comes from the moving mirror. If both of these have same path length, it will result in a higher amplitude, increased amplitude. Both of their crests are added together and their troughs are added together, leading to an increased amplitude and maximum intensity at the detector. Number two is destructive interference. When the path length difference is half integer multiple of the wavelength, destructive interference occurs, resulting in a minimum intensity at the detector. It actually happens when there is a difference of path length. When the crest and trough of the wavelength are different, they cancel each other's effect and then we get a straight line which results in the minimum intensity at the detector. And next is interaction with the sample. The infrared beam generated by the source passes through the sample compartment where the sample is positioned. As the infrared beam interacts with the sample, specific wavelengths corresponding to the vibrational energies of the molecular bands in the sample are absorbed. The remaining light that is not absorbed either passes through transmission or reflects off the sample and reaches the detector. Detectors detect this incoming light, and the detector in FTIR spectrometer plays a crucial role in converting IR light which has interacted with the sample into an electrical signal that can be processed to generate a spectrum. So basic role of detector is to convert infrared light signal into the electrical signal. Next step is interferogram formation. As the moving mirror changes position, the pathline difference changes, causing the interference pattern to vary with time. The detector records this time-varying interference pattern known as interferogram. The interferogram contains information about all the wavelengths of infrared light. This is the basic difference between destructive IR and FTIR, that it can collect all the wavelengths at a single measurement. Next is Fourier transform. After passing through the interferogram, or after the formation of sample and reference spectrums, there is a final spectrum formation which occurs through Fourier transform. The interferogram, which is a raw signal, is processed using a mathematical Fourier transform to convert it from the time domain to frequency domain. The basic function of Fourier transform is to convert the time domain to the frequency domain. This transformation produces an infrared spectrum displaying the intensity of absorption as a function of wave number, as we see in this graph. Transmission as a function of wave number, that is centimeter inverse. General FTIR graph info. FTI are the different regions in FTIR, gives details about different type of functional groups, single bond stretch, triple bonds, double bonds, and fingerprint regions. All these informations about the functional groups can be collected through FTIR. Here is an FTIR graph of nylon. Black lines shows the sample or reference, and red line shows the standard or reference. Now let's see why FTIR is more preferable than IR. Number one is light source. In IR spectroscopy, the light source is monochromatic, while in FTIR it is polychromatic. It can deal with the polychromatic lights. Number two is spectrum acquisition. Single spectrum is produced by IR spectroscopy, while multiple scans can be produced by using FTIR. Scanning speed of IR spectroscopy is low, and FTIR spectroscopy can scan up to 50 scans per minute. Resolution of IR spectroscopy is low and that of FTIR is high, so it is more preferable one. Data analysis. The data that is analyzed by IR spectroscopy is direct spectral analysis, but in FTIR it is Fourier transform FTIR. Sample preparation is time consuming in IR, while in FTIR it is less time consuming. Simultaneous analysis of one or more compounds is not possible in IR spectrometry, but it is possible through FTIR spectroscopy. Interference resolution is very difficult in IR spectroscopy as it deals with the single wavelength at a time, so it is very time consuming to arrange all the data, while it is easier using Fourier transform in FTIR spectroscopy. Now we will discuss about the benefits and drawbacks of FTIR. FTIR has no doubt a huge number of benefits, but there are some disadvantages too. Analysis speed of FTIR is very high. Its sensitivity is very high and it gives detailed spectral information, and it is most importantly a non-destructive spectroscopic technique. Qualitative and quantitative both type of information can be calculated using FTIR, and its major advantage include it is automated process. Its drawbacks include limited structure information, sample preparation challenges because it is difficult to prepare aqueous solutions using to be used for FTIR. Spectral overlap, complex instrumentation, and it is highly expensive. Now moving towards the application of FTIR. FTIR spectroscopy is a versatile technique with a wide range of applications across various fields including pharmaceuticals, environmental sciences, food sciences and forensics. Number 1, chemical analysis. In chemical analysis, FTIR is used for the identification of compounds because it can determine the functional groups present in a molecule, aiding in compound identification. Number 2 is quality control. It is used to verify the purity and composition of the substances. Polymer analysis, characterization of polymers, including identification of additives and degradation products, can be made possible by using FTIR. In pharmaceuticals industry, it is of great importance in drug development. It is used for the drug discovery, formulation development, and quality control. It helps in verifying the composition and purity, ensuring the quality. Polymorphism studies it detect different crystalline forms of a drug, which is very important in pharmaceutical industries as different crystalline forms of drug have different effects on body. In environmental sciences, FTIR helps in pollution monitoring. How? By detecting and quantifying pollutants in air, water, or soil. Climatic studies by analyzing greenhouse gases and atmospheric composition. It can help in microplastic analysis, identifying and quantifying microplastics in environmental samples. In food sciences, it helps to identify the food quality and to control the food quality by detecting adulterants, contaminants, and allergens in food products. Number 2 is food authenticity. Verify the origin and composition of the food items, authenticating its production. Packaging analysis can also be done by using FTIR. It assesses the properties and compatibility of the food packaging materials. In forensics, FTIR is used for crime scene analysis. How? By identifying unknown substances, fibers, and residues and comparing them with the reference samples, we can calculate the values. Paint analysis, comparing paint samples from different sources, and explosive detections, analyze residues from explosions. Other applications include art and archaeology. FTIR can analyze pigments, dyes, and materials used in artworks and artifacts. In geology, it helps in study of mineral composition and it can also help to identify gemstones. In semiconductor industry, characterize thin films and coatings. And this was all about FTIR. Hope so you have enjoyed the video and understood all the topic. Thank you so much for watching.